Good day. I'm glad to welcome you at C3D Modeler workshop. My name is Artem Uvarov, and I'm a mathematical programmer at C3D Labs. Today I'm going to show you some methods of our mathematical kernel and how to use its functionality quickly and simply. I will use a test application to demonstrate the capabilities of the kernel and display three-dimensional models. App was developed by our company. You can see the app interface on the screen now. In this application, you can work with C3D files. It allows you to open, save, and edit the contents of such files. When you open a C3D file, the app creates work window class object. It contains information about the display window and two models, geometric and for displaying. The model from C3D file is represented as model class object. Let's stop on each more detailed. The geometric model is essentially a container for geometric objects, any of which inherits from the item class object. Item class is stored in the kernel like this. Item is geometric model object. Elements such as solid, polygonal objects, local coordinate system, and even object insertion classes inherit from this class. The insertion class is denoted instance in the kernel, and it is represented like this. It stores not only information about the geometric object, but also its local coordinate system as well. With insertion contains an assembly unit as a geometric object. It is represented an assembly class object. Assembly class is stored in the kernel like this. Assembly unit is a model object that combines a set of other objects, but one item belongs to only one assembly unit. For example, let's open the file crankshaft C3D. If you open the context menu of the display window, you can see that its geometric model contains 11 insertions. You can see that there are 60 geometry objects inside the assembly belonging to the first insertion. However, all these objects have some local coordinate system stored in the insertion. It allows you to transform all these objects as answer. For example, move 100 units along the y-axis. Now I'm going to demonstrate this. I move the y-axis by 100 units. You can see that all the elements stored inside the first insertion have been moved 100 units along the y-axis. Among these 60 geometric objects, there is an object called solid, so that is a solid body. This is an object of class solid, which just represents one of the detail elements, while the remaining 59 elements are just auxiliary geometry. It's used to create with solid and saved it, then the model is imported into C3D format. In order to get better understanding of model class, let's look at the code from the function makeUserCommand0. First, let's read the model from the file crankshaft plus C3D into model, an object model class. It is more convenient to use the import from file function to read a model from a file. This function has an output parameter, which is a reference to a model in this case. It is convenient to do this. There are several item objects in the model. So I declare the model, neck the path, and read the model from the file. Use it import from file immediately into the model. In the future, I will use the methods of our test application to render the model. You will have to override them in your projects. These methods make the following. Add a model to geometric model of the active window. Create a flat-faced model based on it, which I will talk about a little bit later. Display the flat-faced model using OpenGL. So I grab the pointer to the active window, remove the old model, add model object to the active window model, fill the flat-faced model, calculate the size of the model, and display the flat-faced model. Now let's look at the result. I'm run the code, and you can see that the following appeared on the screen, such a multicolored model of the crankshaft. Now let's create 6 copies of the first element of the model, arrange them in a certain way, and add them to the model. I will uncomment the next part of the code. I take the first element from the model, duplicate it, put it in an array of new solids, move each solid rotated by a certain angle, and if this object is a solid, change its color. Then increase the angle of rotation. However, these new solids have not been added to the model yet. In order to add them to the model, I need to uncomment the following part of code. You can add an object to the model using addItem method. Let's take a look at the result. And let's run user command 0. As we can see, 6 new items objects appeared in the model. Now let's save the modified model into the file. It is appropriate to use the export into file function to save the model. It has a reference to the model as an input parameter. To show you how to do this, I will uncomment the following part of the code. I set the model into the file, and if successful, the code displays a text message. The model is written to the file, fill it to C3D. Let's take a look at the result. As you can see, the model was successfully written to the file. Let's make sure that it is really written in the file fillet to C3D. I should open it. As you can see, this file contains the model from the previous example. To demonstrate direct modeling methods, I have got the file fillet C3D. Let's repeat all the actions above to the table model from this file. I change the file path to path2 and repeat all the previous steps. Let's look at the result. Now the table appears gray in the center, and 6 colored tables are located around it. Pay attention to the edges with fillets on each table. Now let's remove the fillets edges from each colored table. I'm using the face modified solid function. It allows to make direct solid modeling by modifying solid faces. For this, I uncomment the next part of the code. So I grab a geometric object, check if it is a solid, prepare in advance an array of fillet faces to be removed. Now, in the direct modeling parameters, I define a modifier responsible for removing fillet faces and run the face modified solid function. If have removed correctly, I change the solid to the solid without fillets. Let's look at the result. Now, as you can see, each colored table has no fillets, and the gray table has all the fillets. To demonstrate the result of triangulation in the model, I need a model of plinths. Let's read it from the file using import from file function. It takes the first parameter as a reference to ember item, so I can immediately replace the original geometric object of the model. It's the table in the center with this element. Let's uncomment the next part of the code and take a look at the result. If everything is made correctly, then a table should appear in the center. Instead of the plinths, you can see it. As I said earlier, the geometric model has its polygonal copy to render itself. It contains polygonal copies of each geometric object contained in the geometric model. Each polygonal copy is an object of ember mesh class. MBMesh class is represented in the kernel like this. In fact, MBMesh is container of triangulations. Triangulation is an object of MBGrid class, which consists of a set of points and triangles. Triangulation describes the geometric shape of objects with a certain precision, and it is used to render geometric object, of course. For each geometric MB-item object of the model, I call the gridMesh method, which creates an object of the MBMesh class. A little bit later, I will talk in more details about the parameters of this method. Finally, I render each triangulation of this object. To demonstrate triangulation, I uncomment the last part of the code. So I go through the model objects, check if the object is not null. I create a mesh from it, calling createMesh method on each object. If it succeeds to create an MBMesh object, I render the triangulation of this object. I want to note that one MBMesh object can have several triangulations, so I render each triangulation. Let's take a look at the result. As you can see, all objects are covered with a green grid of triangles. In order to better see the grid, I zoom with 10 and call this command again. These are the triangles that are rendered by OpenGL. Now let's talk in more details about the kernel methods available for polygonal objects. Please pay your attention to the code from user command free function. First, let's open the mesh C3D file containing an object of MBMesh class. I will display mesh using the standard means of our test application. You can also override them. I call the code from the user command free function, and you can see the polygonal object. To make sure of this, I change the rendering mode to one frame. You can see that it contains of triangles. Let's create a new cylinder as an object of cylinder surface class and use the latter to make a polygonal object. To create a polygonal object by a cylinder, I use the calculateMesh method. step data parameter determines the triangulation step along the deflection arrow. FormNode parameter indicates that while creating a polygonal object, it is required to build a surface triangulation and not to build surface contours. So I will uncomment the following part of the code. To create a cylinder, I need to know its local coordinate system, the center of the system, radius and height is required. I build a cylinder. When I prepare the mesh, prepare data for calculate triangulation step, set them, and try to build a mesh using the cylinder. Let's take a look at the result. Before, I need to render the second mesh. You can see that the second polygonal object has appeared. Make sure that this is a polygonal object can be calling the wireframe mode. The fundamental difference between the second object and the first one is that the second object is not closed, and the first one is. Let's call inspect_mesh_closure method for each polygonal object. This method tests polygonal objects for closeness. To show you that, I uncomment the following part of the code. So, if the inspector determines that the first object is closed, it will report that the polygonal object is closed. If the inspector determines that a second object is not closed, it will also report that. Let's take a look at the result. Polygonal object 1 is closed, which is correct. Polygonal object 2 isn't closed, as it should be. Now I replace the second mesh with a closed mesh. Read from the mesh intersection plus 5. I uncomment the next part of the code and also comment out the check of the meshes for closure to speed it up. So replace the mesh 2 with a mesh, read from the mesh intersection plus 5. Let's take a look at the result. You can see where the second object has been replaced with its part of the pipe, which is also a polygonal object. To make sure of this, I call a different rendering mode. This object also consists of triangles. Now, for polygonal meshes, I call create boolean method with the boIntersect parameter, which creates a new polygonal object as the intersection of the polygonal objects, and comment the next part of the code. I also need to add a new object to the model. Let's take a look at the result. You can see the intersection of two polygonal objects. This is also a polygonal object. To make sure, I call the wireframe mode. Change bool intersect to bool difference. Oh, sorry. Bool difference by bool intersect. Let's take a look at the result. You can see the difference is also built correctly. Finally, let's turn to mesh intersection method. It builds the intersection contour of two polygonal objects as an array of polylines. I uncomment the following part of the code. Next, I call mesh intersection function, put the result into an array of broken lines. Now, let's render this array. For this, I uncomment the last part of the code. In order to see only the curves, I comment back on the result of the logical function. Let's see what happens. You can see that the result is 8 broken lines. There is a tool in the functionality of our kernel which allows you to determine quickly collisions of geometric objects, for example, MBMesh polygonal objects. MB collision detection utility tool is an utility to calculate quickly the intersection and proximity parameters of solids. To explain how it works, I need the code from make user command for function. I show you how the detector works using the example of two solids, although a similar result can be obtained for other geometric objects. I will use the standard functionality of our test application to demonstrate how the collision detector operates. The collision detector requires information about the transformation matrix to the global coordinate system for each solid. I will store it in the path matrix type variables. Each variable stores the transformation matrix and the path to the object as an array of simple names. After highlighting the selected solids, I declare the collision detector CDET and the collision detection utility in a class for fast collision detection queries. So I get the first solid, save its matrix in passform variable, and then highlight it. Next, I get the second solid, save its matrix in the passform true, also highlight it. Now I declare a collision detector and then create an intersection request with a function that processes the found collisions. To define a custom collision response, you should create a query that inherits from the CDET query structure. This is a structure of data and callbacks for a collision such query. I create a call query request. It will be processed when you call checkCollisions method, which checks collisions between geometric objects. Call query request must contain a callback function with a specific signature. Let's take a look on the structure of this request. It defines the response to the intersection of objects inside this function. The method here works as follows. You call the query if there is an intersection of faces and the code returns CDET intersected. Then the code renders the face of the first solid in red and the face of the second solid in blue. The code also returns the value cback search more, and it keeps searching further among all the faces to tested solids. Callback function itself is called query func. It has three parameters. Query is the actual collision search query itself. Code is the type of event that occurred as a result of the query. And the CData is a variable that contains information about a pair of objects which are processed as a result of this request. In this case, faces are used as a pair of objects. cback is the return value. So if the request is not null and the faces intersect, then the code renders the face of the first object in red and the face of a second object in blue and keeps searching. If no intersection found, then cback is set to cback void and the code stops searching. Add solid method of the CDET objects adds the solid to the tested for collision and then transformation matrix as well to the global coordinate system. Finally, depending on what value checkCollisions returns, I display the message in the status bar. So if the intersection is found, when the status bar shows then the text found intersection. Otherwise, it shows no intersection. Now, let's take a look at the result of this method. First, I opened the model prepared for collision testing. The model contains two objects, a table and a chair, which intersect, as you can see in the advance. The table leg intersects the seat of the chair. Now I run the code from user command for, select the table, select the chair, and when you see the faces being intersected are highlighted. The edge of the table is red, and the edges of the chair are in blue. The status bar is showing the text found intersection. Let's check if the method is correct by moving the chair by 20 units along the y-axis. I move it in such a way that the objects don't intersect. When I run the code from the user command for again, select the table and the chair. You can see the edges are not highlighted and the intersection isn't found as event sent by the text in the status bar. That's all from my side. Thank you for attention.